Well, good afternoon, everyone. Welcome to this new session of the seminar Dinámica Porteña. It is a great pleasure for me to introduce the next speaker, Luciana Salgado. She's a professor of the Universidade Federal do Rio de Janeiro, Brazil, and she will give the talking about ergodic and geometric aspects of non-uniformly sectional hyperbolic systems. Luciana, please.
Okay, thank you, Sebastian. I don't know if you know, I'm a little bit sick, but I'm gonna try to make me clear, even with its voice. Thank you, all of you, for coming, and especially thank you, Sebastian, for the invitation, and the Dinámica Porteña for the opportunity to be here speaking about my work. And I'm going to talk about some properties that I have I got for sectional hyperbolicity that I have made along the time that between my PhD course and until now, okay? And I'm going to present some results that I've made before and after my PhD thesis, okay? So our setting is we are on an n-dimensional manifold with or without boundary, with dimension n greater or equal to 3. We will denote the space of C1 vector fields on M by this here, by this symbol. I'm sorry. And lambda is going to be a compact invariant set for the flow, and its singularity here is going to be hyperbolic if I said nothing about this, okay? So as usual, we consider an invariant subbundle of the tangent bundle as said to be contracting if we have this kind of decay in the norm, right? It is uniform, and it is expanding if the subbundle is contracting for the reverse flow, okay? So I think that you all know the definition of hyperbolicity for flows. We got three subbundles decomposition of the tangent bundle. The first one, ES, is uniformly contracting. The last one is uniformly expanding. And the middle one is the flow direction. All of those subbundles are invariant, and we have this kind of correlation here. So we said that lambda is partially hyperbolic for X. If we get a dominated splitting, I didn't make the the definition of dominated splitting here, but I think that I've made it before, after this, but I can put here. We get this kind of relation here, dx minus t, f is like this. We have this relation. This is domination for us in two subbundles. There are many definitions, finer definitions of dominated splitting, but for me, this is the dominated splitting. And partially hyperbolic is when we have this domination and this one is uniformly contracted, or this one is uniformly expanded, right? So the first definition I'm going to make here is an extension, is a generalization of the definition of singular hyperbolicity and two-sectional hyperbolicity. The singular hyperbolicity was defined for Morales, Pacifico, and Pujaus, and the two-sectional hyperbolicity by Morales, Metzger, as a kind of hyperbolicity to extend uniform hyperbolicity for flows, including the singularities accumulated by regular orbits. So recently I've made the similar definition, but now I'm going to consider any sectional expansion dimension of expanding subbundle between 2 and the full dimension of the subbundle F, okay? So we say that a subbundle is p-sectionally expanding if each subbundle inside it has the following properties. The dimension is greater or equal to 2, and there are this constant that we have the sectional expansion like this, represented here by the exterior power. Okay, so this is our definition of sectional hyperbolicity is given now. If you say that lambda is p-sectional hyperbolic, if you have a partial hyperbolic splitting where the central subbundle is p-sectionally expanded. Okay, so this is an extension, generalization of sectional hyperbolicity and singular hyperbolicity, because when we have it 2, we have this two-sectional hyperbolicity, and when we have the full dimension of F, we have the singular hyperbolicity, the classical definition. Well, now from now on, I'm going to deal in only to P, except when I need to specify the dimension P. Okay, so sectional hyperbolicity now for us is P sectionally, but I'm going to use P equal to 2. Okay, this is an example of singular and two-sectional hyperbolic flow. It's the geometric Lorentz attractor. We know that singular and two-sectional hyperbolicity is the same in 3 dimensions. Okay, but my definition is based on an example of Turev and Shunikov, where we have 3-sectional hyperbolicity, but we don't have 2-sectional hyperbolicity in a 4-dimension or greater than 4 manifold. Okay, so in this example of Turev-Shunikov, we have a 3 expanding bundle, but we don't have a 2 expanding subbundle, central subbundle. Okay, this is the motivation to make this kind of. Okay, it is also a particular case of singular hyperbolicity, of course. If I have 2, 3, 4, wherever expansion in this central subbundle, of course I have volume expansion. Okay. All right. And in the second year of my PhD, I worked with Alexander Arbieto, and I've made the following definition. The non-uniform sectional hyperbolic set is the one which presents the following properties. It is dominated. We have the composition into subbundles, dominated 1. And we got a negative constant eta, so that for the points inside lambda, we have this kind of it is a mean in estimate. We have contraction in the direction E, and in it is media, mid, I think. No? The word, I think that COVID is not working my brain. Okay, I have two sectional hyperbolic expansion in media, and I have contraction in media here. Okay, this is more or less the what it is
on average.
Yes. Okay, so I'm in this work I have made a relation of the non-uniform hyperbolicity that I have made there, and the genericity of sectional hyperbolic, two sectional hyperbolicity. Okay, so remember that the residual subset is a countable intersection of open and dense sets, and by Baer theory, we have that it is a dense set, okay, in a Baer space, and we say that if a property holds in a residual subset, it is generic. So my first theorem, I think, in my life is the following. Consider an open set of C1 vector fields on M, and suppose that for nx in some residual subset S in this neighborhood, the critical sets, critical here is periodic points and the singularities, okay, is a non-uniform sectional hyperbolic set. So there exists a residual subset A in this neighborhood such that the elements in there have sectional hyperbolicity in the non-wonder set. Okay. In the case when M is three-dimensional, we got something more. We got a residual of sectional X on A. Okay, remember X on A is the non-wonder set is the right. It is the closure of the critical points, and it has a spectral decomposition, like defined by Morales Pacifico. Okay, it is a disjoint union of hyperbolic or sectional hyperbolic sets. So this is indeed easy to see because the work of Morales Pacifico, and because we have no sinks and source in there, because we are in three-dimensional case, so F must be two-dimensional and E must be one-dimensional. So we use the Morales Pacifico result, the dichotomy of Morales Pacifico, and we got the sectional axiom A without cycles. So we got an improvement, and it was a great help comment of Flavio Bidenu. We make an improvement of our first theorem. In fact, there exists a residual set in the vector fields, C1 vector fields, that if the critical set has the non-uniform sectional hyperbolic property, then the non-boundary set is really sectional hyperbolic. Moreover, in this neighborhood, this vector field has a neighborhood that all vector field in there have the closure of the critical points sectional hyperbolic. Okay. Let me see here. I wanted to make a quick comment over the I'm sorry, the proof of this first theorem here. The ingredients of this are the Q closing lemma, Magnet, Ergodic closing lemma, Kuke-Smale theorem, and the non-uniform sectional hyperbolicity. Okay, the non-uniform, I forget to comment that the non-uniform hyperbolicity for flows is an extension of the definition of it for diffeomorphisms made for Castro, Oliveira, Pinheiro, and many people worked on this. And this result is an extension of the result of Armando Castro. And we recover his theorem using our here. So what we have, I think that is better to try. I'm gonna try to write down here. If it's not good, you say me, okay? Okay, you take A as the intersection of S, Q closing lemma, Magnet ergodic closing lemma, and the Kuke-Smale, okay? And this implies that omega x is the closure of the critical points, and it has for all ergodic measure. Really okay, and there for all me, let me write down this better. Here we have it is approximated by convex sum of measures whose support is critical points. Okay, is in critical points. So you take the following subadditive cycle log of dxt restricted to E, and this implies that ft is log of dxt of E right down, and this is continuous. These are continuous functions because the flow is continuous, the bundle is continuous. So, and I know that if X is in this subbundle S, then there exists eta less than 0. Yeah. So that I'm going to put it here, so that the integral over omega x f1 the mu p is equal to 1 over the period of t of p integral this from 0 to tp of f1 over x s p ds, and this is less or equal than eta less than 0. Okay, this is for all periodic points. Okay, because by definition. Okay, so okay, you use the general density, ergodic general density theorem of Magne that I have made a proof in this paper too of this result from Magne, and for all mu we have integral over the non-wonder set f1 the mu is less or equal to eta, which is less than 0. Okay, so I have a proposition with Arbieto, which is in the I'm going to show to you, but is in the in a slide down. Sorry, I'm going to pass the slide, but it's not so good to make. Okay, it's not working. Where is it? Okay. What is it? Sorry. I think that it is here. Yes, this is. If you have a continuous family of continuous subadditive functions and the integral of this mean is less than 0, then we have this kind. Okay, ft is less or equal to eta t. So this is the result that I'm going to use there here, and by proposition we have f1 less or equal to maybe another eta prime, you know, but it's true, and eta prime is also less than 0. So we made the same, similar to are you looking seeing it? Yes, similar to the following ft log of the second exterior power of f inverted. We make the same account and we got the sectional hyperbolicity of the critical points. Okay, this is the idea. Okay, so let me go on. The improvement is we use these accounts, but we have some more details that I'm not going to present here. My point now is look that this is really a consequence of the accounts of the first tier. Okay? So I'm going to make
sorry, in the conclusion, the no wandering set is nonuniformly sectional hyperbolic, or,
no,
or
sectional
just sectional
hyperbolic. Two sectional hyperbolic. Yes,
okay.
we got the uniform sectional hyperbolic.
Yes, yes.
Yeah.
Okay, okay. Thanks.
Thank you for question. Okay. So I'm going to change now for the case of bisectional hyperbolicity. It is more recent, but I would like to bring it to you because all of these kind of hyperbolicity are related with another, okay, each other. So for my motivation to use quadratic forms to characterize many kind of hyperbolicity is based on the work of Leibovitz and Wojtkowski. Leibovitz have proved that if we have a diffeomorphism on a closed manifold such that the quadratic form given by this is satisfy this property, positive, definite, etc., then it is equivalent to have an anosov flow. Oh, sorry, an anosov diffeomorphism. Okay. So basically, in its work, Wojtkowski have made the counterpart of the Leibovitz theorem for flows without singularities. Okay. And during my PhD, I was thinking about it, and I have thought I would like to prove it to sectional hyperbolic flows. And I talked to Vitor, and oh, it's a good problem, and okay, made it. So before to announce the results, I have to put some setting here, some context here. Okay, so I have J, a family of indefinite non-degenerate product forms on the the tangent bundle, and I denote by C plus or minus the open positive and negative vector cones, and C0 is their boundary, okay? And I say that this family of quadratic forms is separated if for a cocycle over a vector field, if the cocycle takes the positive cone inside the positive cone in the next pass, okay, step. It's strictly separated if we take the positive cone with the boundary strictly inside the positive cone. Okay. You already know this kind of property. And J monotone if the function J is a monotone function. Okay, strictly monotone if it is strictly monotone, and isometry, of course, if it is an isometry. So this is the picture of strictly J separation, right? And the counterpart of Leibovitz was proven by Wojtkowski. And he said that if the linear Poincare flow of a smooth flow is strictly J monotone, then it is a nozzle. Okay, this is the picture of the linear Poincare flow, right? And I got a characterization of uniform hyperbolicity, but I needed to consider two smooth families of non-degenerate quadratic forms with index somewhat complementary. Okay, so from Araújo and myself, the maximal invariant subset of a neighborhood is hyperbolic for a flow of index S if and only if we have the flow is strictly separated, non-negative on this isolating neighborhood with respect to J. J has index S, and it is strictly G separated, non-positive with respect to another quadratic form G with this index here. Okay.
Sorry, the index is the stable index?
Yes, the stable index. Yes.
Okay.
Yeah, thank you. It's like the negative inertia index of the quadratic form. So this is a characterization of hyperbolicity by using quadratic forms. And in some sense, it is an extension of the result from Wojtkowski. Okay. So I'm going to show quickly some properties of the quadratic form that I'm going to use after, okay, below. So if we have a separated linear operator, then we can make a polar decomposition of it by one isometry and a J-symmetric operator with positive spectral. This operator R can be diagonalized by a J-isometry, and thus eigenvalues, its eigenvalues have this kind of order here. Okay. Look at this middle relation, and if it is strictly less, R minus is strictly less than 1, and R plus is strictly greater than 1, so we can use it to prove uniform hyperbolicity. Okay. So the operator is strictly monotonous if and only if we have strictly R minus less than 1 and R plus greater than 1. Okay. So joint with Vito, we proved the following result. We got a vector field, a cocycle over the vector field, and the infinitesimal generator of the flow. We take this time derivative of the quadratic form, where this operator J tilde here is like this by using the infinitesimal generator, and we have proved this relation. If the cocycle is strictly J separated, then there exists this function delta such that this is J tilde, okay, is greater than delta x J. By using this proposition, we have obtained the Leibovitz theorem for partial hyperbolic flows. This is the version of the partial hyperbolic flows for the theorem of Leibovitz. Let me show the how to make it. We consider this integral here of the function delta, and we get this for the separated ecocycle. Okay, so the dominated splitting is here. Sorry. Okay, my proposition is the following. We can characterize the different dominated splitting by using the function delta. In particular, if we have a dominated splitting E plus F, it is hyperbolic if and only if the limit when t goes to plus infinity is infinite, and the limit when t goes to minus infinity is minus infinite. Then it is the uniform hyperbolicity that I have proved before. So I've made inside this paper that I've defined the p-sectional hyperbolicity. I have made an extension of the sectional Lyapunov exponents from Arbieto for the case of p, the order p, right? So the sectional Lyapunov exponent is this limit if it exists by using the exterior power. So the estimative of the Lyapunov exponents can be made by using the quadratic forms. If x is separated and the log of the time one forward or backward, the flow is integral. Wojtkowski proved that for an ergodic measure, sorry, we can estimate this kind of relation between the Lyapunov exponents and the pseudo-Riemannian singular values. Okay, so by using this, I'm able to prove the following characterization of dominated splittings based on spectral gap. Remember that set has total probability if for every mu probability measure x invariant, mu of gamma is equal to 1. So if we have a continuous invariant splitting of the tangent bundle on a compact set lambda for a vector field C1 vector field X, then it is dominated if and only if there exists a negative number eta for which the limit of this media minus the limit sup of this one is less than eta, which is less than 0, in a total probability set. This is a full characterization based on ergodic property for dominated splittings for flows. But it is also, I mean, right for diffeomorphisms and okay, but it holds two diffeomorphisms. Okay, but I've proved it before for flows. My question is, how take off the continuity condition of this splitting? Is it possible? I don't know. I'm trying to prove this. Okay. If you know, say me, please. Okay, let's go to prove it. This is the real theorem that I would like to prove today. So you consider the dominated splitting, and because my work with Vitor and the work of Wojtkowski, we know that we have the C1 field of quadratic forms such that X is strictly separated. And then by the previous proposition, we have this order of the diagonalized polar decomposition of this operator. So, moreover, we have this kind of relation between the singular values and the Lyapunov exponent. Okay? Right. So R minus minus R plus is less than 0. And then we obtain, of course, this difference here. Are you hear me? Or I'm not in? Oh, I think that my oh God. I think, yes. Okay.
Please, thanks.
Okay, let's continue. To be continued. The next talk. Okay, all right. Sorry. And so we take a dominated splitting, and by the work of Wojtkowski and Araújo and myself, we have the field of quadratic forms with the properties that I want. So these properties give me this kind of singular values and this kind of relation between the Lyapunov exponents and sectional Lyapunov exponents here. So this difference holds, and of course we obtain this because the maximum of the Lyapunov exponents in the E direction is the limit of it, and the minimum of the Lyapunov exponents of the F direction is the limit sup of this in a total probability set, as we know. So the converse, we suppose that there exists the continuous invariant decomposition, and the number eta less than 0, satisfying this correlation here in a total probability set. So we consider the subadditive family of functions ft by this one, and we apply the limit of the ratio of ft over t, and we obtain this one. So this is less than 0. And we take the Kingman subadditive theorem, use that this is equal to the limit in a total probability set, and the integral is equal to the limit of this integral. So now we use the proposition that I've used before with Arbieto, and then we got this relation here, and it is independent of the point B, a regular one or a singular one, right? And then we make the accounts and got some k that we exponential. We apply the exponential here, and we got the property which we are done. Okay. So I'm going to show some statements of application of this theorem, but I'm not going to prove not anymore. So I can characterize partial hyperbolicity by using Lyapunov exponents and the dominated splitting. Okay, if you have partial hyperbolicity, if and only if we have a continuous invariant splitting, such that we have this one key, which is dominated splitting, and the Lyapunov exponents are negative or positive in a total probability set. And I have a characterization of a sectional, broad sectional hyperbolicity by using the quadratic forms, okay, with the singular values of the quadratic forms here, the operator, the cocycle, the derivative cocycle, okay, in a total probability set. So this is a geometric and ergodic characterization of sectional hyperbolicity. This is the motivation of the title of my talk, okay? So suppose that every singularity is hyperbolic, and then lambda is bisectional hyperbolic if and only if we have dominated splitting, Lyapunov exponents negative in one direction, and sectional Lyapunov exponents in the other direction. This is an extension of a work from me, Arbieto, and Araújo for two-sectional hyperbolicity. I made two bisectional hyperbolicity. And for finish my talk, I want to present a characterization of star flow based on quadratic forms. I think that all you know that the star flow is one of which cannot be approximated by a flow without hyperbolic periodic points, closed points. This is a case of star flow, and I'm going to announce the result. Vector field is a star if and only if we have a neighborhood of the pre-periodic points. This is the set of pre-periodic points. With a field of quadratic forms, this index here is not fixed, okay? We can have change of index of the quadratic forms inside, okay? And the flow is strictly separated on every P inside the pre-periodic points. The singularities are demonotone, which means hyperbolic, okay? And the linear Poincare flow associated to each pre-periodic point is strictly demonotone, which means that the Poincare flow is hyperbolic over the pre-periodic points. So I really thank you for support to be here, even with my voice and with my internet.
Many thanks, Luciana. Thanks, Luciana, please.
Okay.
Some comment or questions?
Thank you, Bruno. You can ask in Portuguese too, in the Spanish maybe. I think that I can. I keep.
Comment or questions? If not, once again, we thank Luciana for the nice talk, please.
Thank you, thank you.
The recording.
I'm going to stop.